Hey Geometry 2 students, Miss Craft here, and today we're going to look at lesson 12.4, which is similarity in right triangles. We have one vocab word for today, which is geometric mean, and that is the average, which indicates central tendency of a set of numbers using their products. Basically, it is statistics for geometry. Okay, I have some steps here for you. First, just how to find a geometric mean, and you will see questions like this on AZ Merit, so it's important to remember. Geometric mean is generally found just between two numbers, and so we set up our ratio first. Our ratio is a over x equals x over b. It does not matter which value you label a and b, because the important thing is that x is going to get squared when you simplify your ratios. So I just called 7a and 15b, and then I set it up as 7 over x equal to x over 15. X will always stay the same. You are not plugging in any values for x. That's what you're solving for. I then multiplied each side by 15, and I got 105 over x equals x. So then I multiplied each side by x to undo that fraction, and I got 105 equals x squared. You then take the square root of each side to undo your radical. And my answer is x is the square root of 105, or approximately 10.25. Okay, I would prefer you leave everything as a simplified radical, but AZ Merit might ask you to find a decimal, so you would just plug that into a calculator and round to whatever decimal place they ask of you. I did another example here where my radical had to be reduced. So again, I just called a 12 and b 25. So 12 over x is equal to x over 25. I multiplied each side by 25 and then multiplied each side by x, and I ended up with x squared equals 300. So I took the square root of each of those and I simplified my radical. This is something you should have learned in Algebra 1 or Algebra 2, whichever class it was that you got to this. So you're going to factor tree. I got 30 and 10, and then I break these numbers down until I get prime numbers. So 10 is 2 and 5, those are both prime. 30 is 5 and 6, so 5 is done, but 6 breaks down to 2 and 3. I'm then looking for pairs of numbers because it's a square root, so I need two of the same number to factor it out. So I have two 2's and two 5's. I factor each of those out of the radical and multiply them together. That's how I got 10 here. And then any number that doesn't have a pair just stays inside the radical. So my answer as a simplified radical would be 10 root 3. There are two ways you can check this. Number one, you can find the decimal. So I would plug into a calculator the square root of 300, and it gives me approximately 17.32. To check and make sure that I did my radical simplification correctly, I would do 10 times the square root of 3. It also gives me about 17.32, so you know that you've done that math correctly. I left you one question here if you chose to find geometric mean on your own, and I would recommend that you do so because this whole lesson uses geometric mean, but this is definitely the most basic. Okay, below that we have two geometric mean theorems. And what I wrote in box 1 is really just some extra information, just in case you forget, I guess. So the first one is the geometric mean using the altitude theorem. And I will let you read that, but the important thing is that the altitude is the geometric mean, the last statement here, of the lengths of the two segments of the hypotenuse. So the two segments of the hypotenuse are what gets broken up. So when I draw the altitude from the right angle to the hypotenuse of the original large triangle, my broken up hypotenuse becomes x and y. The height or the altitude is h, and so this is saying that h squared equals xy. What I wrote below this is the extra information because really you're just using triangle similarity. So you need to understand that should you forget any of this, now, there's not always enough information to use these ratios here, but sometimes there is, and so it's nice to fall back on if you forget. And that is, I can always rewrite my triangles, and that's what I did here, and then do the long leg over the long leg equal to the short leg over the short leg equal to the hypotenuse over the hypotenuse. So just looking at my corresponding sides and solving for lengths that way. The nice thing about the geometric mean theorems is it allows you to skip a whole lot of steps because it's just two really short formulas. So knowing that the height squared is equal to the hypotenuse's segments multiplied together saves you tons of time. Okay, the next theorem is the geometric mean leg theorem. And this is saying same thing. I'm going to draw the altitude from my right angle to the hypotenuse, but then the length of either leg of the original triangle, so A, is equal to the geometric mean of the hypotenuse and the segment that's right next to the leg you're using. So the segment next to A is x, so that's why I used x here. So A squared, the leg of the original large right triangle, is equal to x times c. So the whole hypotenuse is c, and then the leg that's next to A, is multiplied by that. I can also find B using the same method, but segment y, the broken up segment y, is what's next to B. So I would do B squared equals y over the whole, the hypotenuse c. Okay, both of these formulas are used in the examples below, and I try to leave plenty of examples for you to do so that you can attempt if you so choose. Okay, so applying the geometric mean theorems, I'm going to go ahead and move to just the examples. This one here, really basic. I'm just showing you the altitude theorem that was presented above. So we're finding the measure of the altitude, and you're given the broken up lengths of the segments. Okay, so x squared equals 2 times 13. 2 times 13 is 26, so I take the square root. 26 can't be broken down. It's 13 and 2, which is, they're both prime numbers. So x is either equal to the square root of 26 or it's approximately 5.1. Okay. The next example is the same exact way. You're finding the altitude, and you've been given broken up segments. What I would like to point out is example 3 here. You're still solving for the altitude, but instead of being given both broken up segments, you're given one broken up segment and the whole, which means you would need to calculate this missing piece GH, which is not difficult. You're doing basically segment addition postulate backwards. So 12 plus 4 gives me 16, so 4 is the missing piece. Okay, the next two examples that I did, the first one uses the geometric mean leg theorem. So I am solving for both legs here, x and y. When I solve for x, I'm using 4 because that's the leg next to x, and then the whole original hypotenuse, which is 6. I obviously had to add those together. You were given the broken up parts, which is 4 and 2. So x squared is equal to the leg next to x times the whole hypotenuse. So 4 times 6, which is 24. I then took the square root, and the square root of 24 can be simplified. So 24 is 8 and 3, 8 is 2 and 4 is 2 and 2. I have a pair of 2's, so I was able to pull that out. And then a 2 and a 3 that have no pair, so they get multiplied together and stay in the radical. So x is 2 root 6, or again, you can write that as a decimal, which is 4.9. Okay, when I solve for y, I'm using 2 instead of 4 because that's the leg next to y, but it's the same thing. Y squared is equal to 2 times 6. So 2 times 6 is 12. Again, this is a number that can be broken up, so 12 is 4 and 3. 4 is 2 and 2, so I have a pair of 2's. My pair gets pulled out, and then the square root of 3 is what's left that can't be simplified, or it's also approximately 3.46. Okay, the next and last example that I did here, you are using both the leg theorem and the altitude theorem. So just differentiating which one goes where. I left the third example because it uses the leg theorem twice and the altitude theorem. So it should be good practice for you to apply everything. But this one, I solved for x first. Remember that the altitude, which is x, the height of the triangle, is equal to the broken up hypotenuse multiplied together. So x squared is equal to 3 times 8. That's 24. I didn't break it down again because we just did the square root of 24, which is 2 root 6, or approximately 4.9. When I solve for y, which is the leg theorem, I'm doing y squared is equal to the segment next to that leg, which is 3, times the whole. The whole is not given, so 3 plus 8 is 11. That's where 11 came from. So I have y squared equals 33. And then I take the square root of that. 33 can't be broken down. 3 and 11 are both prime numbers. So it's either the square root of 33 or approximately 5.74. That's all I have for you for lesson 12.4. Again, this one is pretty common on AZ Merit, so I would recommend going through these and doing the practice problems so that you are prepared when that test comes. If you have any questions, please feel free to send me a message on Canvas. Thanks.